Breakfast.
The Radio Wammo Breakfast.
Live from the New Scientist Labs,
Janine Young.
newscientist.com.
It's a good time to talk new science with Janine Young in Melbourne City. Good morning, Janine.
Good morning.
Morning. Now, we will be talking about renewable oil or biofuels. But first up, let's talk about what science gets wrong sometimes and then admits that they get wrong, Janine.
That's actually one of science's strengths. Who would have thought that, people actually are reasonably good at saying, actually, we had a theory and we got it wrong. But that's sort of really the point of science. The whole idea is that you come up with an idea, you test it against the available evidence that you have, see if that evidence stacks up, and if it doesn't, you change your theory. That's fundamentally what science is. And so over time, people have worked out that, maybe the Earth doesn't go around the sun after all. That kind of thing. But when you start getting down to some more detailed sorts of theories, there's some really interesting ideas that are starting, or indeed have been, overturned.
Hang on, the Earth does go around. The Earth does go around the sun, right?
Oh, I meant sun going around the Earth.
I just thought suddenly occurred to me. Hang on.
It's early in the morning. Can I say that? Can I hide behind that? Does that work?
It's like people have worked out that the Earth is not round.
I'm moving on to talk about what I meant to be talking about because I know I got that wrong and I've just admitted it and I'm not doing it again.
Sure.
Okay, if anyone studied chemistry or even had any kind of exposure to it in school, you'll have been told about your atomic number and your atomic weight for every element. The atomic number doesn't change. The atomic weight is all about how many protons and neutrons are inside the nucleus of each element. We've been told that this is immutable. It can't change. That's just the way it is. Except for the fact it's not. Isotopes are different variations on the theme, if you like. So it's all to do with how many neutrons are inside the nucleus, and that can change. So, for example, hydrogen can in fact vary quite a bit. It goes from about 1.007 something to 0.1008. That's actually quite a big difference, and it can have practical dimensions. For example, in tropical areas, the heavier isotopes of hydrogen that form water as part of the water cycle fall to Earth a lot earlier than some of the lighter isotopes. And so it means that the waters are slightly heavier in tropical areas than they are at the poles. Interesting. There's a lot of things that are different. They're slightly saltier at the poles as well, at the equator as well. Very interesting. So it was driving chemists nuts, apparently. There was practical problems in actually working with it. So what they've done with a number of different elements, including lithium and boron and sulfur and nitrogen, is actually given them an upper and a lower banding for what their atomic weight can be. And they've had to go through and actually make these changes at the highest possible levels in chemistry to try and make this a workable solution. Because instead of being hard and fast and saying, no, this is the way it is, they've had to become a bit more flexible to accommodate what they've found since. So again, it's not that they got it wrong so much, it's just that they said actually there's a different type of stuff going on here than we first realised.
Okay, yeah.
So people can admit their mistakes, for want of a better word.
What else have science got wrong, Janine?
The traditional groupings of mammals and birds and reptiles and fish, again, things we've learnt in school and you think they're pretty straightforward. They're actually not if you use a different type of naming. Cladistics was brought up in the 1960s by a guy called, what's his name? Willy Hennig. He was German. And he was an entomologist, so he studied insects, and he'd been looking at how animals related to one another in an evolutionary sense, and actually looking at their shared characteristics and genetic relationships to each other. So it was a very logical, it was German, a very logical way of looking at how each animal, bird, fish came into existence. Now that's okay when you're looking at things like mammals and birds, because they have one common ancestor, which means that they were able to have just one consistent group. But the common ancestor of lizards and crocodiles and snakes and tortoises and the reptiles that we know about actually also gave rise to mammals and birds. So there's no consistent reptile branch. They're contaminated, if you like. And so they don't actually have a group of their own. So technically, in cladistics, there is no reptile group. They have an amniotes is the name of their grouping, and that's just not the same. It doesn't mean anything to the ordinary person. Amphibians are just the same, so frogs and toads and newts and the like. Their group also includes all the tetrapods, which were extinct four-limbed vertebrates. So that's sort of down the mammalian line. And so if you use cladistics, you don't have amphibians and reptiles anymore. Yeah. So they've just disappeared out of the naming patterns. Yeah. On a practical day-to-day basis, people don't use this. It doesn't work for practical purposes. But if you use this process, then you sit there and you go, whoops, we have no reptiles.
Interesting.
It's an interesting way to look at the world.
It is very interesting. Let's move along now to biofuels, and let's not talk about old biofuels, because biofuels have been around a long time, and we know that there have been some good biofuels and some bad biofuels where they've taken up areas where you could be growing food instead. Let's talk about some new innovations in biofuels.
You're right. The first generation biofuels caused all sorts of problems and spikes in food prices because they were derived from corn. And they were using corn for biofuels when they should actually have been using it for feeding people. And they were using arable land that would again have been useful for feeding people. The second generation ones used inedible types of crops, but it required far too much energy to be able to get to the basic building blocks of what was necessary to make these biofuels. The third generation ones are relying on cyanobacteria. So these are creatures that are able to reproduce under carbon dioxide and sunlight. Basically, they photosynthesize. There's particular types of them that are able to produce alkanes. Now, alkanes are the basic hydrocarbon building blocks of things like diesel. The simplest is methane, and then it kind of gets bigger and more complicated from there. Researchers in the United States in particular believe that they have been able to manipulate these cyanobacteria so that they actually produce these alkanes into very conveniently sized blocks of about 13 to 19 units, and they can secrete them. Instead of ordinarily what they would do is to keep them within their cells or maybe to secrete a little bit, they've actually tinkered with them so that they can secrete them in reasonably large amounts. I think they've got up to 90% efficiency. This is what they're claiming. We don't have any evidence at this point yet to be able to compare this against, and no one's been able to reproduce their results. Obviously, this is very commercially sensitive because the competition in biofuels is fierce. People want to make a lot of money out of this, and they can see that there's a big future ahead. But being able to convert 90% of the photosynthetic energy coming in, the carbon dioxide and the sunlight and the light, and then secreting it so that you can actually have that come to the surface and easily skim it off. Sounds almost too good to be true. But this company, Joule, is claiming that this is what they can do. There's other companies that are also trying to set this up using different techniques. Some are using bacteria that live in the earth, and they're actually finding different ways to be able to do it. So whichever system is going to work is good if you can make it work, but the problem with these sorts of systems is that growing anything like cyanobacteria is really unpredictable. All you need is a tiny, tiny perturbation in the system just to tinker it. Maybe the sunlight might change one day, maybe it might go a degree or two colder, and the entire system falls down because the bacteria aren't happy. And that there have been companies that have tried pilot plants and failed over the longer haul simply because of the vagaries of growing bacteria. Wow. So they can get really tricky.
Sounds like early days, that's for sure.
But hopefully promising. It would be good if you could actually have something that grows on carbon dioxide and sunlight, because if you can take waste carbon dioxide and pump that into your system, then that's less carbon dioxide that needs to be captured or buried or somehow dealt with in any other way. So if it can be put to a good use, it sounds like a win-win.
Indeed. Well, those two stories we've just been talking about, you'll find in the New Scientist magazine coming out next week, and also online as well at newscientist.com. Thanks very much, Janine.
See you next week.